And now for the final speaker of this session, Yann from IRCAM, who will present his paper, Phoneme-to-audio alignment with recurrent neural networks for speaking and singing voices. So it's time to start.
Okay, thank you. So, dear speech community, I'm very happy to be here to share with you this work on phoneme-to-audio alignment with recurrent neural networks for speaking and singing voice, which was conducted by Axel, Roebel, and myself. I am Yann, a PhD candidate at IRCAM. So I will directly dive into the context of this presentation, which deals with alignment system. So just the general goal of any alignment system would be to synchronize several representations expressing diverse aspects of a common underlying information. So in the case of music-related data, for instance, well, one could say that for a given musical piece, it would be possible to align the music score or the available lyrics with some audio signal representing a given performance. This is basically what you can see here for score following, for instance. So how do we do that? So I will present a general overview of the kind of alignment system we aim to develop and deal with in this presentation. So first, you will obviously have some kind of audio data on which you would apply a model. This model will generate some hidden states or hidden representation of your audio data, and then from this hidden representation, you will try to synchronize it with some data to align. This will be thanks to a decoding algorithm that you will be able to retrieve your final synchronization between your audio input and your data to align, your final alignment. So this very general overview will be the key for this whole presentation for both the state-of-the-art and for our model. So regarding the related work now, and especially a starting point, the data representation, for the audio data, there are typically the temporal signals to represent them or the spectrograms, so a time frequency representation for this. And for the data to align, well, they are typically of symbolic nature, but they can be musically relevant data, such as the score itself or note sequences, or they can be linguistics, such as the lyrics directly, or phonetic transcripts, so translation of the lyrics in some alphabet, in some phonetic alphabet. In this work, obviously, we are interested with the spectrogram as audio input and phonetic transcript for phoneme alignment. So now we talked about the different kind of modeling approaches. So in literature, basically in alignment literature, hidden Markov model often coupled with Gaussian-Merkle model are really ubiquitous. They are maybe one of the major breakthroughs in alignment literature. And more recently, for phonetic alignment, very interesting results were appeared with deep neural networks. And this work is concerned with the later approach, so we aim here to develop a learning model. So that being said, the question that raises now is how to train this model, and meaning what kind of objective function for the training of this model. Here again, in literature, there is different approaches. The first one would use the categorical cross-entropy as the loss to minimize. So from this point of view, in fact, the alignment challenge would be a classification problem. You want to classify for every time frame the correct phoneme that is appearing. So great performance have been denoted with this approach, but in fact there is a need for an existing alignment, a pre-trained alignment, pre-existing alignment for the training data. And in fact only few datasets would provide such perfect annotation. So a second approach makes use of a specialized cost function referred to as Connectionist Temporal Classification, or CTC, from which in fact the alignment is derived from a transcription task. So CTC would output per frame probabilities on a given set, on a given alphabet, here phonetic alphabet, and will be able to decode a sequence from this probabilistic generation. The loss will measure that the decoded sequences will be close to the target sequences. For this approach, you won't need to have a precise alignment from your training data, which makes a key difference with traditional HMM and the first approach with categorical cross-entropy. That is why we decided to develop here a CTC model, so choose the CTC as objective function. So for a visual example of CTC, taken from the website of Anun, you would have an input like speech or a spectrograms, and once you have generated your probabilities, the CTC will output for each time frame some character from a given alphabet, plus a blank label, referred to here as epsilon. Then you will get rid of this blank label and merge repeated label, and you will have a final prediction, and you will measure if this prediction is close to your ground truth. So As I said, we apply a model to the audio input to generate some hidden representation. For HMM, we really talked about hidden states. Here, due to the stochastic nature of CTC, we rather talked about label posterograms or label posteriors, which would look like this. So if input, you would have some mel-spectrograms with given time frames. You would obtain labels posteriors with exactly the same number of time frames, but probabilities for all your phonetic alphabet. So now that we have our label posteriors and that we know the data we want to synchronize with it, this is our goal to develop a decoding algorithm to map both of them, the posterograms, with the known data to align. So usually, the first step of a decoding algorithm would be to compute an accumulative cost matrix. We will talk about this later in the presentation, and then apply the decoding itself on this. So for the decoding, you could have a greedy strategy or a beam search decoding strategy. Then you could also apply some kind of language model that can be learned or derived from n-grams. And you could add some additive heuristics, such as lexical constraint or forced alignment constraint. In this work, we will choose to use beam search decoding coupled with forced alignment constraint to ensure that each phonetic label will have correspondence in the final alignment, which can be directly retrieved thanks to the decoding step. So this is what it would look like, our system for phonetic alignment. You would have your spectrograms in input, generate your posterograms, then compute your cumulative score matrix, and finally obtain your alignment. So for each label in your sequence would have a starting time and an end time. Here the phonemes are presented as sequences, but in fact we'd rather convert them as an activation matrices to manipulate them as a 2D inputs. So the main question at stake now is precisely what kind of CTC model and how do we generate relevant posterograms for the task of alignment. And this is basically where I will present our current proposal in this, the proposal of our paper. So the question here again is how to generate the label posterograms. So one kind of model architecture is relevant for with CTC for generate precise alignment. So the very starting point is to use the mel-spectrograms with a derivative in times, data and delta features, and go through a spectral encoder composed of bidirectional LSTM, and go through CTC decoder to produce probabilities constrained by the CTC loss. So this architecture is the most basic you can think of, and in fact it can struggle only to transcribe and will definitely not be suitable for alignment. So we had to go further, and given the fact that CTC coupled with attention has been shown to greatly improve transcription task, we decided to generate another branch, a second input, referred to as context encoder, with two context studies. So one spectral, so reusing the spectrograms as second input to generate a self-spectral attention, or the non-aligned phonetic transcript to generate a phonetic attentions, so that phonetic sequences, so that each phoneme could be associated with the relevant spectral region as well. So now that we have these two encodings, so spectral and context encoding, we can multiply them, then generate attention weight thanks to a softmax with a learnable dense layer, then an attention context that can finally be concatenated to the original branch to generate the posterograms constrained by the CTC loss. So this attention mechanism has the strength of working for any length of the phonetic sequence and for any length of the spectrograms. So, however, currently there is still no guarantee that the probabilities will be coherent in time, because precisely CTC is only a transcription cost and it would not penalize misalignment. As long as the correct sequence is retrieved, there is no guarantee that there will be a correct alignment for your purpose. So now on, what we wanted to do is to reinforce the temporal coherence in the CTC prediction. To do so, we decided to add a spectral decoder aiming at reconstructing the original spectrograms from the posterograms itself, seeing the posterograms as some kind of hidden representation of the input data. So the spectral decoder will be constrained by the reconstruction cost, like L1 between the spectral estimate and the original spectrograms. And this is what we call temporal coherent reinforcement, because necessarily to have a good reconstruction from the probabilities themselves would have to be aligned in time, coherently aligned in time. So this is our main proposal of this paper. Now that we have trained our model to retrieve final alignment, this is how we do. So we would have some spectrograms. You would have non-aligned phonetic transcript, You would apply your trained model on this to generate your post-diagrams. Then you would compute your accumulative cost matrix. So the recursion rule is given here. This is based on Vertib's algorithm. And so for a given label and a given time frame, basically there are several contributions. You would have the previous score, so at the previous times for the same label, the label before it, and the blank label in between. So you will only have some allowed transitions, and it will be weighted by the current label emission, which is given by the post-diagrams. Now that it is done, you would apply a beam search decoding to retrieve your final alignment, your final synchronization between phonemes and time. So we will compare our system to a recent baseline developed by Yann Foster in 2020. That, in fact, this paper was used to jointly proceed to speech separation and derived phonetic alignment from the very similar attention mechanism directly from the attention weight. Because the attention weight, in fact, turns out to have a good shape to directly apply beam's dynamic time warping on them, so that if the attention weight are relevant, you could retrieve directly an alignment from them with beam search decoding. So we will compare our system to this baseline in the following. So far, this approach has been the best GNN-based alignment system for speech using non-aligned phonetic sequences as input. So I will now present our several experiments with both systems and for several data sets, because we are interested in speaking and singing voice in this work. So for the speaking voice dataset, we will use the famous timid dataset for speaking voice, multi-speaker, and 5 hours long. And for the singing voice dataset, we will use a dataset from IRCAM, Chanter RT, that deals with singing voice with a single singer for 1 hour and a half long. So first thing we can say is that most phonemes, so all of spoken phoneme and half of singing phonemes are shorter than 200 milliseconds. And clearly for the singing database, there is a bimodal distribution centered at 1 second. That's because the singing voice dataset was originally thought for singing synthesis, and so vowel were asked to be held long by the singer. So here I will briefly detail our parametric setup, but I won't be too long on this. So there are our general hyperparameters to compute spectrogram frames of 16 milliseconds and 16 kilohertz. And most interestingly, all decoders and encoders are based on 2 by LSTM with 512 units each. Most interesting thing is our complete objective function that will be minimized throughout training with validation and early stopping. And this complete objective function would be a weighted sum of the CTC constraint and the recurrent constraint. So here there is a key parameter acting as a trade-off between several losses. This parameter lambda is studied here. So you would have our model with spectral attention and phonetic attention. And you can see that if lambda is too small, well, the CTC loss is not sufficiently constrained, so performance are not that good. And there is exactly the same for if lambda is too large, because the reconstruction cost would dominate the CTC and your system will not perform alignment. We can see interestingly that for both system and both speech and singing, the default value for lambda equals 0.1 works best. So this is what we choose in the following. Now we compare our results to the state of the art. So the baseline in blue is first our implementation, then the best system reported in the reference, and the MFA, which is the Montreal post-aligner, here again reported in the original paper. Then there are our system with phonetic attention, spectral attention, and no attention. So first we can see that the attention mechanism is really important, because without it, performance degrades a lot. And when comparing our system to the baseline, we are better both in speech and singing voice in mean time, in mean imprecision error. This everything holds true for the median imprecision as well when comparing our system to the baseline. And note that there is no correspondence for the baseline in singing because it was only speech-based. So here, a brief summary of our system. We see that the system with phonetic alignment performs the best, and that aligning singing voice is way more challenging than aligning speaking voice due to the larger diversity encountered in sung phonemes. Some perspective of this work will be now to analyze real music performance with background music, for which maybe investigate joint separation and alignment tasks would be relevant, and run various analysis towards singing style analysis as part of the ARTS project that has funded this work. As well, we will try to deal with long sequence alignment, so entire song, and to do so, we will take ideas on automatic speech recognition and automatic lyrics transcription literatures For example, for speech, try to do audiobooks synchronization. Here are some bibliography. I thank you for listening, and should you have any question, I would be very happy to answer it. Thank you.
Thank you, Yann, for your presentation. So now it's time for question.
I have two questions for your work. So at first, I say that you build your models based on recursion loss and also reconstruction loss. But in the later experimental tables, you comparing the alignment performance. So I would like to that in your experiments, you just train the data on without the alignment annotation and evaluate it on the dataset with the alignment annotations, right?
Exactly, yes.
Okay.
In order to have result and quantify our work, we still need database with precise alignment. So yes, in our training we don't use the alignment, we only use the sequences. But for evaluating an alignment error, we have the precise alignment for Teytaut is aligned.
Okay. So my second question is that you said that you are calculating the attention. So how you do that? You are using attention-based STM or transformer or something else?
Yeah, in fact, the attention is really only first a multiplication between the two encodings, so our two branch, then a learnable dense layer, so to do basically a multiplication between the context encodings and the audio encodings. And then we are, to have good shapes, we've multiplied this by the original context encoding to have attention context that we only concatenate with the original branch. So this is only, the attention mechanism, in fact, is only really a dense layer, a learnable dense layer. And
try like transformer or not?
No, I haven't.
Okay.
I haven't. That would be interesting, definitely.
Any other questions? Maybe for remote, there's a written question. Did you try to use not only one single audio for train and or inference, but few singers in the same audio?
No, we did not. That would be interesting as well. That's not something that we tried so far, given we not have such databases, so we did not so far.
And there is another written question. If you drop the first alignment rule, would the system be able to correct labeling errors, or would that cause more labeling errors?
Can you repeat, please?
If you drop the first alignment rule, would the system be able to correct labeling errors, or would that cause more labeling errors?
Yeah, it would be much more complicated because when we don't use the forced alignment constraint, where the forced alignment constraint is very useful to help the system in the beam search decoding to really compute, not only to compute the cost matrix and to retrieve the best path within it. So if we don't use this constraint, and if the probabilities are not extremely precise, this may link to a very imprecise alignment sometimes. So yes, this constraint is very important, and if we don't use them, this is a bit more complicated.
Okay, thank you. I will invite one raised hand. We experience these difficulties with the raised hand, so maybe I will ask a remote speaker to write their question directly. Any other questions? Okay.
Very interesting work. I was wondering, I have two questions actually. So did you also examine different beam sizes in the CTC loss if you see better like performance if you increase the beam search? Or
in fact, yeah, we tried. So here in this work, for this evaluation, we used a 50 beam size, and we've tried 100 and 200, and there were no significant. I think it's because the database are short audio segment with short phonetic sequences. So in fact, pretty easy to find the best alignment in an accumulative cost matrix if well shaped. So 50 beam size was enough to obtain a relevant result, and using a greater one was not that interesting. So we did not.
Okay, thank you. And one more question about, so when you were testing the model, you were looking at the phonetic alignments which were alphabet-based, right? Alphabet-based from the timid. I'm talking about the symbols in the phonetic level.
Yeah.
So did you also consider IPA symbols, for example? Sometimes there could be stress symbols or elongation marks.
Yeah, there has been some pre-processing on the timid phoneme vocabulary. Basically, we especially with ending phoneme and stuff like that. So yeah, there was some pre-processing in order to reduce the size of the phonetic alphabet, and especially with the pauses, for instance, and based on energy. And,
okay, thank you. Very intensive work. Thank you.
Any other questions? No, probably. Oh. Yes. Yes, sure. Yeah.
About how the reconstruction, loss, how does it affect speed of the decoding or of the process? Because I assume that the CTC is a pretty fast algorithm, and if you have some measurements of real-time factor or anything like that?
For real-time or for runtime?
Like any measurement of
actually, without the reconstruction code, with the reconstruction code, there's for these small databases, once again, the system takes approximately 5 hours to train and to be applied on a single GPU. And if we don't use the reconstruction code, this would be obviously a much this would be, I think, half time reduced, but you would have poor performances. So, and runtime would. For runtime, I have no measurement, but for training time, it's about 5 hours for separate databases. So for each database, it would be 4 hours.
A little bit. One more question: is it open source or is it the code available somewhere?
Oh, we have not released the code, but yeah, this is something that we like to do, especially with as part of this project, to release a system, inference-based system, to align any kind of audio databases. But it will require a pretty strong system that could deal with many kind of sung phoneme and speech phoneme. And for now, we don't have that. So we aim to release it, but we don't have that yet.
So if there is no further question, maybe we can stop this session. So thank the speaker again.